Hey grade nines, just hanging out with my paper towel roll and my neodymium magnet. Neodymium, one of those rare earth metals that helps make good magnets. Um, that you guys might remember for that video that we watched back when we learned about chemistry. And so, what we notice is, well, what I've noticed is that just holding this paper towel roll produces no current. So right now I'm measuring current in milliamps on this multimeter. I have a wire wrapped around this paper towel roll, and it's connected all up to my multimeter. And what we're going to do is I'm just going to put the magnet inside the paper towel roll and shake it back and forth, and hopefully we see something on that multimeter. So here we go. Down, up. Oh, it got stuck to the. Oh, I saw some numbers. Okay, normally it's at 0. I am able to get a very, very small amount of current by moving this magnet through, as the magnet goes through this paper towel dispenser. So copper isn't a magnetic material, but what is happening and what we're seeing here is a magnetic field causing electrons to move. As the magnet goes through this paper towel roll, it is causing electrons to move, causing them to flow, and as soon as electrons begin to flow, we get something called an electric current that we measure. We only measured a very small amount, but it was still measurable. So what we're starting to realize is that electricity and magnetism are very much related. And so we have this, well, I have this Eternity flashlight, and there's no batteries in it, but it operates by the same principle. So there's a magnet inside it and a coil of wire, and to power it, you just need to move, well, I guess might not be the most practical flashlight, but if you don't have batteries, it becomes the greatest thing ever. So I'm going to turn it on, and I'm just going to shake it back and forth. Let's see if we can build up enough charge to get this light shining. Oh, there we go. And then probably as I stop shaking it, it's going to get dimmer and dimmer. There's probably something in here called a capacitor, which is holding that charge for just a short amount of time. So yeah, I can already see it's getting dimmer. It's dimmer than it was before. But yeah, again, it's just powered by a magnet moving through a coil of wire. Something else I want to show you. So we have this copper tube, and inside it there's two magnets, and they fall, well, I think they fall slower than they would under the force of gravity. And the reason why that's happening is because as the magnets flow through this copper tube, that produces an electric current, which in turn produces another magnetic field. And so the magnetic field that is produced opposes the direction to the magnets inside, so they fall quite slowly. Well, slower than they normally would. Okay. So this whole idea of this, or this very simple idea of a magnet flowing through a coil of wire, or if we can think about it in the opposite way, a coil of wire, we could also put that around a magnet. This is how all of our, well, in a very simple way, this is how all of our electricity is generated in this province and in Canada. It's all about spinning a magnet in a coil of wire, or spinning a coil of wire around a magnet or close to it, so we can get those electrons moving. Let's talk about it a little bit. Nines, you've just seen a magnet make electrons move. So we just need to do this on a massive scale in order to get power to your home, so you can watch this video right now. So in order to do this, there's a couple ways of doing it. We might use a thermoelectric generator, which is just we're gonna have to burn something. We're gonna have to burn coal, natural gas, some type of fossil fuel, and that's gonna give us the energy we need to spin something called a turbine. And so once we can get that turbine spinning, that's gonna spin a loop of wire in a magnet, or a magnet around a loop of wire, as you guys have just seen, and that's gonna force electrons to move. So a couple chapters ago, we talked about energy being converted from one form to another. So we're just taking that chemical energy, changing it to heat energy, and changing it into electrical energy, and the mechanism by which we're doing that is called a turbine. Going back in time a little bit, 1820, Hans Christian Ørsted, he noticed, first person to notice that, he had a compass near a wire, and he noticed the compass needle deflect. It moved when it was near that wire. And this was kind of like the first clue that electricity could produce a magnetic field. And the exact opposite happens as well. A magnetic field can also produce an electrical field as well. And another key discovery was when the current was reversed, the needle also moved in the opposite direction. And so there was a relationship there as well. I'm fresh out of electromagnets, but I will have to build one of these and do a separate video of it. But basically, we can use electricity to create a magnet in something that is otherwise not magnetic. And so if we have some type of iron core, and if we can wrap a copper wire around it, and then if we can get a current flowing through that copper wire, we basically create an electromagnet. And there's a couple ways that we can increase the strength of it. One is by increasing the number of coils, the number of times we're wrapping that copper wire around the magnet. The second way is by increasing the amount of current. In order for it to work, the core must be conductive as well to some degree. It's not going to work. You couldn't wrap a copper wire around a pencil and create an electromagnet. It wouldn't work. It needs to be some type of conductive material. Metals are good conductors, as we learned in chemistry, so something like an iron nail will work well. Okay, so this is kind of what we were talking about before, making electricity. I guess making isn't the best word. We can get a current flowing through the use of magnets. So magnet going through a coil of wire will produce current. And like we just talked about, most power generation is done this way. So everything from like thermoelectric coal-fired or natural gas-fired generating plants, hydropower is also just using water to spin a turbine. As long as we can get something spinning, we can create electricity. Wind turbines are also going to use this same principle, spinning a turbine, wind turbine. It's turbines right in the name. I'm going to say nuclear power too. Just using nuclear power, get some steam, that steam spins a turbine, you got electricity. Okay, in Alberta, I think this is like 2010 data, so it's a little outdated, but I don't think that much has changed. Maybe a little bit more natural gas, but I think it will change as we move away from coal. So at that point, a large amount of our electricity was produced using coal. A decent chunk of the pie using natural gas, and then we got some hydro, wind, imports. That's just getting energy from another province or maybe even the States. But yeah, so things are starting to shift. People are starting to move away from coal. Natural gas is a bit cleaner, so that is one that seems pretty popular in Alberta. And also renewables are getting more popular too. The amount of electricity that is needed in Alberta, there's the Alberta energy regulators, that are constantly predicting how much energy the province needs every single second of the day. It's almost like they have to guess like 10 minutes ahead or even like a minute ahead all the time of how much energy to produce, because energy made from these thermoelectric generating plants, we can't store it. Well, there is one way, but there's no big huge battery anywhere that's storing any excess power that we're making. So we don't want to make too much or else it'll get wasted. We also don't want to make too little or else there's going to be like a neighborhood blackout and the lights are going to go off, and that's not good either. So it's almost like we just have to make just enough, just maybe slightly more than we need, so that we can keep the lights on everywhere. But it's not as much of a guessing game as you might think. It is kind of predictable. And here's kind of like here's a chart from December 7th, 2010 of like when people are sleeping, a lot of the lights are off, a lot of the businesses are shut down, and so there's much less power that's needed. But around 5, 6, 7 o'clock, people start waking up and the lights start coming on, people start cooking their bacon, and more electricity is being used, and then it kind of levels off throughout the day. Everyone's at work, and then there's a bit of a spike around 5 and 6. Everybody's getting home, turning the ovens on, baking the casseroles, and all that good stuff. So we're using a lot of electricity here. TVs are going on, and all that sort of thing. And so there's a bit of a spike here, and then it decreases as people go to bed. So, and a lot of days follow this pattern. Maybe the weekends look a little bit different. Maybe holidays look a little bit different, but a lot of weekdays will look something like this. The type of current that we have in our homes is alternating current. It is just a type of current that is, well, in order for electricity from move to place, it also takes energy to do that. We talked about the idea that we lose a little bit of, there's a lot of resistance in wires, and we lose a little bit of that power as those electrons move from place to place. But AC power, alternating current, does a lot better job of moving electricity over bigger distances than DC or direct current. So this is what we use in our homes today, and yeah, it's basically those electrons are like moving back and forth. They're alternating in our wires. DC generators, they have something called a commutator, which is, you can read more about it on page 314 of your textbook, but it's basically just a device that allows the current just to flow in one direction. But yeah, maybe that's all I'll say about that. That's it.